Hey guys, this is Professor Janacek, and I want to talk about tangent planes. Let's let f be differentiable at the point ABC with the gradient at ABC not equal to the zero vector. Then we can define the tangent plane to that surface, f of x, y, z equal to 0, at that point ABC. Is the plane through this point ABC orthogonal to the gradient? And it's given by this equation here. Now, I want to talk a little bit about that equation. Notice the coefficients, partial with respect to x for the first one, partial with respect to y for the second one, and partial with respect to z of the third one. All of those are evaluated at that point. Remember, that is our gradient. It's really this vector made up of those partial derivatives. Also, make sure you understand what's going on here. This tangent plane is orthogonal to that gradient through this point. So, make sure you understand that this gradient is orthogonal to the tangent plane at that point. Right, so make sure you can visualize what's going on. You've got a tangent plane, and then we're looking at something that's orthogonal to that. All right, and that is how we get our coefficients. Now, if you remember back when we first found equations of just planes, not necessarily tangent planes, but planes, we used the normal vector for those coefficients, and that's exactly what's happening here. You can say that it's orthogonal. You can say that it is the normal vector. That's exactly the same idea. So this isn't really a new topic. We're just calling them different things, and now we are using this idea of the gradient. All right, so let's try some examples. Let's find an equation of the plane tangent to x squared plus y squared minus z squared is equal to 0 at the point -4, -3, 5. All right, so first thing, let's go ahead and let f of x, y, z equal to this x squared plus y squared minus z squared. Remember, we want f to be equal to 0, and we have this is equal to 0, so we're ready to go. So we can go ahead and just name that as our function f. Then we can determine the partial with respect to x. Again, just looking at this, treating y and z as constants. The partial with respect to x is 2x. The partial with respect to y is 2y. And the partial with respect to z is -2z. And now what we need to do is to determine what these partials are evaluated at our point. So the partial with respect to x evaluated at this point gives us -8. The partial with respect to y gives us -6, and the partial with respect to z evaluated at our point is -10. All right, and now I think we're ready to do this. Again, remember, this is orthogonal to this is orthogonal to our tangent plane, and that's exactly what we want. In order to determine an equation of a plane, we need this normal vector. All right, so that's what we're using. We are using the vector -8, -6, -10. All right, so now we end up with -8 times x minus -4 minus 6 times y minus negative 3 minus 10 times z minus 5 is equal to 0. So again, all I'm doing is using this vector and that point. We can, of course, clean this up quite a bit. That gives us negative 8 minus 32 minus 6, let's see, negative 8x minus 32 minus 6y minus 18 minus 10z plus 50 is equal to 0. We can clean this up even more. Negative 8x minus 6y minus 10z is equal to, oh, that's equal to 0. Lovely, lovely. I do notice, so there we have an equation, but I do notice that all of these coefficients are both even and negative. So let's go ahead and multiply both sides of this equation by a negative 1/2. And that gives us the equation 4x plus 3y plus 5z is equal to 0. Much happier with that. The numbers are a little bit smaller and all positive. It's always nice to work with positives, right? There we go, an equation of the plane tangent to x squared plus y squared minus z squared equal to 0 at negative 4, negative 3, 5. On to example 2. Let's find an equation of the plane tangent to z equal to 2 plus 2x squared plus y squared over 2 at 3, negative 2, 22. And I've already done the first step here. Looks like I was thinking ahead. So the first thing you'll notice I just took this equation, did a couple of things. One, I set it equal to 0. I want it to be equal to 0 because remember up here, f needs to be equal to 0 before we get started. Always going to work out much easier that way. So I got it equal to 0. The other thing you'll notice I did, instead of y squared over 2, I wrote that as 1/2 y squared. That's just going to allow me to use the power rule a little bit easier without losing anything. All right, so there we go. Now we will simply let f equal to this bit right here. Again, remember f is supposed to be equal to 0. So we'll call this part f. Then we can take the partials of f. With respect to x, we get 4x. With respect to y, oh, we just get y. With respect to z, that's just a negative 1. And now we can evaluate those partials at our point 3, negative 2, 22. Right, so the first part with so the partial with respect to x gives us, what is that, 12? The partial with respect to y evaluated at that point is negative 2, and the partial with respect to z at this point is simply negative 1. All right, so now we are ready to find the equation of the plane. Again, we're using kind of 12, negative 2, negative 1 as our normal vector. So we could say over here, I guess we could have said that, our normal vector. Actually, that's formally that is the gradient. So this is really the gradient, but it is a normal vector. So lots of these things are very similar in concept. All right, so moving on, we now can write our equation. It is 12 times x minus 3 minus 2 times y minus negative 2 minus 1 times z minus 22 is equal to 0. We can clean this up a bit. Now, following what we did previously in example 1, we would write this as 12x minus 2y minus z is equal to, what is that, 18. That's what we get. Watch those positives and negatives. However, and that is completely acceptable. That is an equation of the plane. However, I noticed that my original equation is z in terms of x's and y's. So we can go ahead and do that here as well, writing this as a function z in terms of x's and y's. We get z is equal to 12x minus 2y minus 18. So staying consistent with this problem, I will go ahead and finish this equation there. All right, well, there you go. Enjoy.